continue with our foray into complexity theory with Sid Redner. I've met Sid many years ago. I think I met you by going to give a talk at BU, and then we sort of talked a lot, and then I invited you to give a colloquium here, God knows, 10 years ago or even more.
I think it's more like 20 years ago.
20 years ago, holy cow. Okay, so let me tell you a little bit about Sid, in case you don't know him. So he got his PhD at MIT in 1977, did a postdoc at Toronto for a year, and then joined the Boston University Physics Department, where he stayed for 36 years, has been chair of the department about 3 times, and he's also been a visiting scientist in different places, including an Ulam scholar at Los Alamos in 2004. He's been to Toulouse and in France, and to the Université Pierre-Marie Curie in Paris. So very good taste in places to go visit. And a few years back, he moved from BU to the Santa Fe Institute, which I think makes perfect sense given what Sid does. You know, his research interests are mostly on non-equilibrium statistical physics, and he applies the toolkit of statistical physics to all sorts of different phenomena, as you'll find out today. You know, he's been working on the structure of complex networks. He's developed many new models and new methods to understand network structures. He also has devoted a lot of effort to formulate and solve physics-based models of social dynamics. And he continues to investigate problems of phase ordering kinetics, so a little more standard StatMax stuff, let's put it that way, and understanding of zero temperature coarsening in Ising and Potts models, okay? He has a great enduring interest in diffusion processes and applications in the natural world, and in stochastic transport processes in disordered porous media. So you can see that he really has been probing around many different kinds of physical systems using tools from statistical physics. As a result, he's published more than 250 articles, and he has 2 books. He has a monograph called A Guide to First Passage Processes, and he has a graduate text written with Kaprivsky and Ben Naim called A Kinetic View of Statistical Physics from Cambridge University Press. And he is a member of the editorial board of the Journal of Informatics, pardon me. And he is an associate editor for the Journal of Statistical Physics and a divisional associate editor for PhysRev Letters. So that's quite an extensive curriculum. And today, Sid is going to talk to us about basketball. Is basketball scoring just a random walk? You know, I want to see how he's going to connect all these dots. It's going to be lots of very interesting. And just to finalize this conversation, so Sid is currently a professor at the Santa Fe Institute. I think you've been there, what, 4 or 5 years? I'm not quite sure.
6 years now.
6 now. Okay, that's it. Okay, Sid, the floor is yours. Thanks.
Okay, well, thank you for a very generous introduction. I really appreciate it. And it's nice to be sort of back at Dartmouth. I remember my visit there a long time ago. It was very pleasant. So today, what I'm going to be talking about is in collaboration with with a former PhD student, Alan Gable, and then 2 collaborators at the University of Colorado, Marina Kogan and Aaron Clauset. And the basic question we want to address is, can we use the tools of statistical physics to understand the statistics of basketball scoring? And in particular, is basketball scoring a random walk? So let me tell you the punchline. The punchline is the answer to this question is yes. But let's get there. So first of all, when you look at a basketball game, this is what most people see. I just want to turn down because it's kind of weird music coming up. So when you watch a basketball, so that's LeBron James, you see incredible feats of athletic daring do. I mean, I could only dream of what these people can do. Like, I could never even touch the net, you know, jumping. I just can't jump at all. And look at this. It's just amazing. So you know, if you are a typical basketball fan, you see these incredible athletic feats. It's truly amazing. There's one more dunk that's going to happen here. However, what I see as a statistical physics is very different. This is what I see. Flipping a coin over and over again. And if you have very good eyes, that's a 5 ruble coin. It was shot in a Moscow hotel room. So that's my cinematography experience. So the thing is that while I find basketball athleticism truly amazing, I find basketball impossible to watch because it's nothing, to me, it's nothing than just watching over and over again, flipping a coin. Is it going to come up heads? Is it going to come up tails? And so let me now present some evidence to try and convince you of my perspective on what basketball is all about. So we have roughly 10 seasons of NBA basketball data. We collected basically the score as a function of time in a game. And so we have for these several tens of thousands of games, we have score as a function of time. And we want to try and analyze this data productively to learn what we can from it. So here is a typical trace of a basketball game. This is Chicago-Denver on November 26, 2010. And so we start out the game 0-0. And for those of you who know nothing about basketball, the only thing you need to know is that teams score a basket, and the basket can be worth 2 points or 3 points, or sometimes even more, depending on exceptional circumstances. And so the score gradually increases until at the end of a typical NBA basketball game, the score is roughly 100 to 100. And so here we have a plot as a function of time over 48 minutes or 2,880 seconds, the score difference. And in this particular game, Denver raced out to a huge lead, almost 20-point lead, and they maintain the lead. So this is the first half. They extend the lead at the beginning of the second half. And then Chicago mounts this furious comeback. And then there's a lead change. By the way, can everyone see my cursor? I forgot to ask that.
Yes, we can see
very
well.
Good. Okay, so there's a lead change here, and then Chicago's leading for a while, and then there's another lead change. So the game at the end is sort of exciting. And finally, at the very last second, Denver wins by a small amount. So the question I want to ask is this trace a random walk? So let me try and present some evidence to argue in favor of this. So the first thing that one sees about basketball is that the scoring rate is roughly constant as a function of time. So I'm plotting here the probability that there's a score at any given minute of the game. And so roughly speaking, there's a rate of scoring which is roughly 0.03 per second, which means that once every 30 seconds, there is a score which kind of comports with what you know. And forget about these weird things at the beginning, because at the beginning of the first half or second quarter, the ball is inbounded. And so it takes a little bit of time before you can ever score a basket. So the scoring rate at the very beginning is 0. The scoring rate at the very end of a quarter or a half is large, because if you score a last second basket, that corresponds to a large scoring rate in that last 1 second. So, one should throw away the first 1 second and the last 1 second, and the rest of the data looks fairly constant. So that is conclusion number 1. There's a fairly constant rate of scoring throughout the game. Another important point is that the scores are randomly distributed in time. And so what I'm looking at here is the time intervals between successive scores of a game. And so I'm plotting logarithm of the probability that there's score after a time delay delta t. And the thing about basketball, at least NBA basketball, is that there is a thing called the 24-second clock, where you have to attempt a shot that actually hits the backboard within 24 seconds, or you lose possession of the ball. So this means that there is an incentive to shoot a basket before 24 seconds. So the thing is that up to about 24 seconds, it takes time to actually set up your play and to maybe make the shot. So there's a low scoring rate with a very small time interval. But then beyond 24 seconds, if I'm plotting it on a semi-logarithmic scale, it fits very beautifully to a simple exponential. And in fact, if you look not just at either team scoring, but you just look at the scoring rate of a single team, it's the same exponential distribution. And so we can conclude from this that the probability that there's a time delay delta t between successive scoring events has an exponential decay, which is a hallmark of a Poisson distribution, which suggests that scoring is a random process. And the only difference between single team scoring and either team scoring, you see there's an overall factor 2 in the overall scoring rate. So that's the second piece of evidence. Next, and this is perhaps the most important, is this notion of the hot hand. I mean, I think that we all have this feeling, and certainly sports casters will always say this, well, this guy is hot, give him the ball because he's really hot. And the question is there such a thing as a hot hand, that when Stephen Curry gets hot, that he, one should give him the ball because he's going to sink every basket? And at least as of 1985, the data seemed to show that there was no evidence of any hot hand. So there's a very famous paper by Gilovich, Vallone, and Tversky that actually analyzed NBA basketball scoring data by hand, actually, and they found no evidence for a hot hand. And so now, using the data that we have, we looked at the same question. So we're looking at correlations between successive scores. Are they correlated or are they not? And if they're not, then we have more evidence in favor of like a random walk picture. So here, what I'm showing is these little blue lines are meant to be like scoring events. And there's an average time between scoring events if we average over an entire game. So if a team is hot, that means that the scoring events come fast and furious. And if a team is cold, that means there'll be long periods of time between successive scoring events. So if there were correlations, then we can look at the difference between the average time between a scoring event and the instantaneous time between the kth and the k plus first scoring event. And so if there is correlations, then this delta tk should be large in streaks, and it's going to be, the absolute value will be large in streaks. When your team is hot, delta tk will be large and will be very negative. When the team is cold, this delta tk will be large. And furthermore, if a team is hot, that means that lots of scoring events happen very in close succession, which means that delta tk and delta tk plus 1 should be very highly correlated. So when the index of which scoring event you're talking about, when these indices are close, then these delta tk should be highly correlated. So if there was correlations, that's what we should expect to see. And so now we do like sort of what we normally do in condensed matter physics. We look at the correlation function between the kth scoring interval and the k plus nth scoring interval. So if there were correlations, then this correlation function as a function of n should, decay in some way slowly as a function of n that says that there is some correlation. And by the way, the denominator here is just to normalize things nicely. So this is just the correlation between the kth interval and the k plus nth interval. And so if they're correlated, we will get a large value for the sum. And if they're not correlated, we'll get nothing. Anyways, so let's look at the data. And the data is incredible. When we first found it, it was like we were very happy because it shows there's basically no correlation. Once you reach n equals 1, the correlation drops to a value of roughly 2% and stays constant for all values of n. So this is another piece of evidence that there's no correlation between successive scoring events. Finally, the last piece of information that helps, my argument that this is a random walk picture is to look at the linear growth in the score difference variance. So what I'm plotting here as a function of time is the difference between the score of team A minus team B quantity squared, which is nothing more than the mean square displacement of a one-dimensional random walk. So for a pure one-dimensional random walk, sigma squared, we know goes linearly in time. And you see that over most of the time of the game, this variance is growing like the square root of t. So this is perhaps the most naive picture to try and argue that what we're seeing in the scoring in NBA basketball is nothing more than a random walk. So preliminary conclusion from those 4 pieces of evidence is that basketball scoring looks like a random walk. And at this point in my talk, I've given this talk to basketball hotspots like University of Kentucky, UCLA. Usually by this point of the talk, like the basketball players in the audience are like, they're apoplectic. They're yelling at me. Unfortunately, you can't yell at me virtually, but let me now try and give a little bit more meat to some of these preliminary conclusions to try and argue that it really is a random walk. So let's look for more evidence. And it turns out that a really good way of finding this additional evidence is by looking at lead changes. And lead changes are nice because, first of all, lead changes when the game is exciting. If it's a blowout, then you don't want to watch a blowout. But if the lead is changing all the time, it's the lead changes that are the most interesting part of the game. And so let's look at some pieces of some statistical features of these lead changes. So for example, the kinds of questions we can ask is how many lead changes occur? How long does one team lead? When does the last lead change occur? And when is a lead safe? Which is of course very important for real-time betting, especially if you live in England. So let's look first of all at the number of lead changes. So what I'm plotting again is score difference on the y-axis is a function of time. And so the score is team A is winning, team B is winning, A is winning, is going to win the game. And there are points where the score is tied. These are the lead changes. So the first natural question you might ask is, what is the number of lead changes? And it turns out that for evenly matched teams, the number of lead changes M scales as square root of N, where N is the number of scoring events in the entire game. And again, to give you a feeling for numbers, I see there's a question. Well, okay. I guess Marcelo will tell me if if it's important. Anyways, so to give a feeling for numbers, if there's a score every 30 seconds and the game is 48 minutes long, there's roughly 96 scoring events. Each score is roughly 2 points. And so it corresponds to a game which ends with 100 to 100. So if there's roughly 100 scoring events, then the number of lead changes should be of the order of 10. So and first of all, why do I say square root of n? And so let's do something very simple from the theory of random walks or one-dimensional diffusion. Here's the probability distribution of one-dimensional diffusion. Pxn is the Gaussian as a function of, the Gaussian e to the minus x squared over 2n with the square root of 1 over 2 pi n. So we ask, what is the probability that I'm actually at 0, which is where a lead change occurs? That's going to you substitute x equals 0 and you get 1 over the square root of n. And what we want to do now is compute the total probability over the length of the game of being at the origins. We just have to integrate 1 over root n up to the number of lead changes. And when we integrate 1 over root n, we just get square root of n. So this is the naive estimate for how many lead changes should occur in a basketball game. 10.
Sid, can you hear me?
Yes.
So the question, it's interesting. It says, why would a basketball player or fan be upset that their game is a random walk? What is the implication? No skill, no significance of a win or loss? That's the question.
Well, okay. I mean, I was going to say this a little later on the talk, but let me say it now, which is that why would we say that, or why do I argue that it's a random walk? So the thing is that if you look at the NBA basketball players, these are people who were the best players in their high school. They were then recruited to the best colleges. Then they got in the NBA draft. They got, selected by an NBA team. They made the team. They're perfectly coached. They have like a yoga coach. They have a nutrition coach. The point is that these players are so good that any systematic differences are basically arbitraged away, and all you are left with is random walk fluctuations. In addition, they have like the best strategies. They have the best coaches. So if there's anybody who develops any kind of competitive advantage, like, Steph Curry, when he came into the league, he started sinking 3-pointers that nobody else could imagine. But what's happened is now other people are developing the same kind of 3-point skills. So as soon as someone finds some competitive advantage, it very quickly gets arbitraged away. So yeah, I mean, so to me, it's very natural, but some people do get upset when I say something like it's only a random walk. Does that
wait? Yeah, that's fine. Another one. How do you explain the fact that multiple teams have have a hard winning streaks. Yes,
High
year
winning
after
streak.
years. Like,
Yeah, yeah, yeah.
teams like Chicago Bulls with Michael Jordan kind of thing.
Right, right. Well, so let me put that a question in abeyance because I'm going to address it a little bit later on in the talk. So whoever asks a question, if you're
No
not happy
problem.
with it later on, ask it again. Okay. So first point about basketball, and again, for those of you who really watch basketball games, you'll say, well, this can't be a random walk because there's one basic feature, and that is anti-persistence. When a team scores a basket, then the possession of the ball goes to the other team that was scored upon. And this corresponds to an anti-persistent random walk. And the word anti-persistent means that if team A scores, then it's more likely that team B will score next. And it turns out if you average over all NBA basketball games, then it turns out there is this persistence probability of 0.35. So that is, if team A scores, team B is likely to score next with a probability of 2/3, and team A is going to score with a probability 1/3. So what that means in terms of a random walk trajectory is that if you move away from the origin, you're moving, say, to the right, the next step is more likely to be to the left, and vice versa. If you make a step to the left, your next step is more likely to be to the right. And clearly that's kind of a force that's pushing you towards the origin. And so one might expect that in real NBA basketball games, the number of lead changes is larger than 10. And so it turns out that, using the same random walk argument, the main difference is just that because of this anti-persistence, it reduces the diffusion coefficient by a factor of p divided by 1 minus p, which is basically a factor of 2. So the number of lead changes turns out to just scale by, there's an additional factor of roughly square root of 2. So instead of 10 lead changes, it's roughly 14. And in fact, one can carry this analysis a lot further. One can look at the distribution of the number of lead changes, just not the average number. And it turns out that George Weiss in 1994 wrote a very beautiful paper where he showed that the probability that there are m lead changes in an n-step random walk has this Gaussian form. And so if all that matters is that the diffusion coefficient is renormalized by a factor of p over 1 minus p, we just stick that in there. And so this is our prediction for like the number of lead changes in an anti-persistent random walk. And now on this slide, what I'm showing is three things. One is this very simple Gaussian, anti-persistent Gaussian random walk process. The triangles are the actual NBA game data, and the circles are just a simple simulation of a Poisson process with this anti-persistence built in. And you see that we can fit the actual game data really, really well with only one parameter, this anti-persistence parameter. So that's the number of lead changes. Another thing which I really enjoyed working on, and I think it's really cool, is like how long does one team lead? So again, here we are back at our Chicago-Denver game. And again, Denver is leading almost the entire game, then Chicago has a comeback, Denver is leading, Chicago has another comeback, and finally Denver wins. So every time that this trace is above 0 corresponds to when Denver is in the lead. So these little green line segments are the time over which Denver is in the lead. And what I want to ask is, well, if we now add up these little green segments, we can ask, what is the length of this green segment compared to the length of the entire segment? This is the fraction of time that Denver is leading. And then we can average over all NBA basketball games and ask, what is the fraction of time that any one team is in the lead? So let me tell you what I first thought when I was confronted with this question, which is, well, the teams are evenly matched, they're changing leads all the time. So half the time one team is leading, half the time the other team is leading. And so that's what I thought. And so if I look now at the probability distribution of the fraction of time that one team is in the lead, and so the fraction goes between 0 and 1, and so clearly this function should be symmetrical about 1/2. So what I thought was this: it seems very natural that most of the time the teams are leading half the time in any given basketball game. And so here, if I could see the audience, I'd even ask for people's opinion. But since I can't, I'm just going to go to the punchline and tell you what the data shows, because the data shows something completely different. Instead of being a peak near 50-50 lead time, there's a peak when one team is leading or the other team is leading, and there's a minimum when there's 50% of the team leading. And in fact, one nice thing about this particular data is that we can then fit it to a very simple analytical form with 0 fittable parameters. There's something called the first Arcsin Law. And it turns out that this probability of one team in the lead fits this thing called the Arc Sine Law function, 1 over square root of t, capital T minus little t, where capital T is the length of the game and t is the absolute time in the game, and a 1 over pi. And so in fact, even the amplitude fits more or less perfectly. And in fact, for anyone who's learning probability theory, this is perhaps the easiest advanced topic in probability theory, the existence of this Arc Sine Law. So the point here is that even though you're flipping a coin equally likely heads and equally likely tails, and you play for a certain amount of time, the amount of time that one guy is in the lead is typically peaked at the extreme of either one guy is leading all the time or the other guy is leading all the time. So this is, I think, a very surprising result at first sight. And another nice feature about this is that one can fit the actual game data with no adjustable parameters. So this, I think, is a really strong evidence that this is a pure random walk process, because this first Arcsin Law is one of the fundamental results from the theory of one-dimensional random walks.
Hey, Sid, I have
Yep.
2 more questions from the
Sure.
audience here.
Sure.
First one is from Ethan, a grad student, who asks, how do you define evenly matched?
Evenly matched teams?
Yeah.
Okay, well, that's coming. Give me another 15
okay.
minutes and I will
No
talk
problem.
about that.
And there is another one from the fellow who asked the first one, do different strategies, that is teams shooting lots of 3-pointers versus mostly scoring near the basket, affect how closely the scores follow the trends you're describing?
Well, okay, I have no answer to that question, because all we have is the score as a function of time.
Not the details of the score. Yeah.
Yeah, we do know, like, the scoring event, sometimes it's a 2-point play, sometimes it's 3 points. And in fact, the maximum number of points in any given scoring event is 7 points, where someone attempted a 3-point play and there was a flagrant foul and then a technical foul and then another technical foul. But we're not looking at that kind of fine-grained detail. That's right. Beyond like what we can do in this kind of a study.
Okay.
All right. So let me now look at the time when the last lead change occurs. And this is now getting into the domain where it's really statistical physics, or maybe it's probability theory, because we can also calculate this analytically and fit it and look at how well it fits the data. So let's suppose that there's a game trace, and at some point the score was tied, and finally one team wins by an amount X. And we can ask, where is this time? Is this time close to the end of the game, or close to the beginning of the game, or is it in the middle? And what is its probability distribution? And again, when I was first thinking about this problem, I thought, well, evenly matched teams, there's lots of lead changes. So the last lead change should occur close to the end of the game. And boy, was I wrong. So first of all, let's now calculate this. When is the, if there's a last lead change at time little t, there's 2 conditions that have to be met for this to be the last lead change. First of all, we have to be at the origin at time little t. And then we have to guarantee that the rest of the trajectory stays above x equals 0 for the rest of the game. And the way that we can guarantee that is that we say, well, let's reverse time and start at some unknown position x. The trajectory must come exactly to 0 at time capital T minus little t. And it can't come before, it can't come after, it has to happen exactly at this time. This defines what's known as a first passage path, because if you first hit at a time capital T minus little t. So this is a time reversed first passage path that starts at a distance x away and hits the origin in this remaining time t. So this thing is just the Gaussian probability evaluated at x equals 0. This guy is a more complicated expression. And so let me do a little digression to derive it, because it's kind of cool. So for those of you who have been exposed to random walks, the first thing you probably remember or learn about is, where is a random walk? So again, we have this Gaussian probability distribution for the position of a random walk. But what we're asking now is a different question, is that when does a random walk first hit a given point? So here's the question I want to ask. When does a random walk starting at position x0 first hit the origin? What is that probability distribution? And it turns out there's a very simple way of calculating this first passage probability that relies on the image method of electrostatics. So here is a space-time representation. I start with a random walk at position x0, and it does some random trajectory, and at some particular time, it hits the origin. And I want to compute the probability for it to hit the origin for the first time at this particular time, which means it can't hit earlier. Later doesn't matter, but I've got to not include trajectories that hit at any earlier time. And how do I compute those trajectories, throwing away any trajectories that got there earlier? And the simplest way of doing it is by the image method. You start with an anti-random walk at position minus x naught. And by definition, the Gaussian spread of this guy and the Gaussian spread of this guy, if this comes with a minus one amplitude, these things will exactly cancel at the origin. And so this guarantees that there's no chance of reaching the origin before. And so the probability distribution of a random walk which stays above the origin and hits for the first time at time t is the sum of the Gaussian probability distribution starting at x naught minus the anti-Gaussian starting at minus x naught. And from this probability, we now can compute the flux, the diffusive flux to the origin. That's what I define as the first passage probability, in the sense that if you hit the origin, you remove from the system, and then you look only at what's left hitting the origin. And so it's simple algebra. You can compute this, and you get this very nice functional form. And this has two amazing consequences, this first passage probability. The first one is the eventual hitting probability, that is the time integral of hitting at any given time, is 1. So for those of you who are not familiar with this fact, it's really quite amazing. You start with a random walk at position x0, and you say, will the random walk eventually hit the origin? And the answer is yes, for sure. But you can ask, how long does it take to hit the origin? And that answer is infinite. So even though you hit the origin for sure, the time is infinite. And this infinity in the time comes because in the long time limit, this becomes 1, and you see there's a t to the minus 3/2 tail. That's a long time power law tail, such that the first moment is infinite. This dichotomy between you're sure to hit the origin, but infinite time to do so is what makes random walks and diffusion such a lively and alluring and seductive field of physics. And it's been that way, ever since, over the past 100 years. Okay, enough digression. So now we have the first passage probability. And now we want to, what we need to do to calculate the probability distribution of where this the probability distribution of time t is the following, is we want to do a convolution. We want to convolve the return at time t, which we already found, and the time reversed first passage time. And we want to integrate over all possible positions of the unknown final position x. And then there's a factor 2 because team A could have won or team B could have won. And this is an elementary integral. And lo and behold, it's the Arcsin Law yet again. So this is called the second Arcsin Law. And so the second Arcsin Law is the same as the first Arcsin Law in its mathematical form, but it asks a very different question. In fact, there's a third Arcsin Law, which is what is the probability distribution for when the largest lead occurs? And lo and behold, it's the same functional form. I did not know about it when we did the study, but I'm sure that if we looked at where the last lead change was, at the time of the largest lead, we would also see the same thing. Anyway, here is the data for the time of the last lead change. And so again, it's not peaked, it has this sort of 2-peak shape. And what I'm showing now is the actual data. And here is a fit to it by doing a homogeneous Poisson process. And you see there's some really little glitches at the end of the first quarter, second quarter, third quarter. And if we do an inhomogeneous process where we don't use the average scoring rate as the input to the Poisson process, but we use the instantaneous scoring rate second by second in the game, we can actually account for all these weird glitches in the data. So again, where the last lead change occurs is most likely at the very end of the game or the very beginning of the game. Unlikely it's going to happen in the middle of the game. And there's the Arcsin Law prediction. So you might ask, and certainly I ask this, why are there 2 peaks in the distribution of times for the last lead change? And so to give you a flavor for this, let me plot like a score difference as a function of time. But it turns out when we're dealing with a random walk, which is a scale invariant process, it's much better to look at things not as a function of time, but as a function of logarithm of the time. Because for those of you who are familiar with random walks, you know that there can be many, many lead changes and then a big gap between lead changes, and the time between successive lead changes is growing like the square root of t. So if I put it as a function of log t, these long excursions are kind of the same length of time. So if the game ends here, then the last lead change happened just before the end of the game. And so the last lead change is near the end of the game. However, here's another trace. And here we say, well, the last lead change is here. And you might say, well, that's close to the end of the game, except for the fact this is on a logarithmic scale. On a logarithmic scale, any finite distance is way, way back in the past. And so one really has to work hard to engineer things to have something near the middle of the game. So this is a kind of hand-waving argument to show that the last lead change should happen near the beginning or near the end. All right, last thing on this particular topic, when is a lead safe? So if you're into real-time betting, you might say, well, here there's the last lead change, and we want to ask, what is the probability that if there's a lead change at this particular time, that it's safe, that the team is going to continue leading for the rest of the game? So let me define Q, LT, the probability that a lead of size L is safe when there's a time tau left in the game. And we know how to do this now because we've learned about first passage. So the probability that a lead is safe is 1 minus the probability that a lead is not safe. And a lead is not safe if we can make a first passage path from L to the origin within a time t. So we just have to integrate first passage probability up to time t. And we know the analytical form of F. And so it's a simple algorithm. I mean, it's a simple formula. In the case of evenly matched teams, and I'm going to come to the unevenly matched teams momentarily. So after you do all of the simple algebra, you get the error function as a function of z, where z is kind of like the natural scaled measure of the length of the lead. It's the lead size divided by the square root of the time left in the game. And so here's what it looks like. The probability that the lead of scaled size z is safe. So the bigger the lead change, the more probability that the lead is safe. And to give you a feeling for numbers, if you have a 10-point lead with 8 minutes to go, that corresponds to this scaled lead size of like 1.13, 1.15, and it corresponds to a probability that the lead is safe of 90%. Anyways, here is the NBA data. Here is our simple error function prediction. And for those, when I give this talk and not in the United States, nobody has any idea what's going on here, but perhaps many of you have heard of Bill James, the inventor of sabermetrics, who've made all kinds of metrics for baseball. He had his formula for the probability the lead is safe, and this is his formula. Here's the data, here's our formula. You decide what you like better. Okay. So what I would say at this point is that with all this additional evidence, the random walk hypothesis seems more plausible. But I'm not done yet, but there's a few buts here. And so let me go through some of the buts, because these are perhaps the most interesting aspects of the talk. So the first point is that clearly basketball scoring is not a pure random walk. It's an anti-persistent random walk. After team A scores, the same team scores next with a probability roughly 1/3. And we've already seen how that affects things, and it basically doesn't affect anything at all. But then there is this feature of a basketball game. The last 2.5 minutes of a basketball game are anomalous. So let's look at that. And for those, I can say that, when I was living in Boston in the mid 80s, and there were these incredible NBA finals between the LA Lakers and the Boston Celtics. They were so intense. And the thing about them, and for those of you who are basketball fans, you probably know this, is that the first half goes by quickly. This third quarter gets a little bit slower. And if it's a really tense game, it might take half an hour to finish the last 2 minutes of the game. And in fact, the last 2.5 minutes are completely anomalous, and it's a different game altogether. So if we again go back to the scoring rate, I argue that it's roughly, if you throw away the first second and the last second of the quarters, it's more or less constant. But notice here, there is this huge increase in the scoring rate in the last few minutes of the game. The other thing is that if I look at this linear growth in the score difference variance, well, it's linear up to around here, and then there's something weird going on at this stage. So to try and ferret out what's going on, let's look at the actual score difference distribution at different points in the game. So here is at the end of the first quarter, the score difference distribution, which is a Gaussian as we might expect from a random walk picture. And here I'm plotting the probability as a function of the scaled deviation divided by the time, so that data for different times of the game should lie in the same universal curve. So at the end of the first quarter, it's Gaussian-like. The end of the second quarter, it's Gaussian-like, and it exactly fits the first quarter data. So everything seems very nice and random walk-like. Here's the end of the third quarter. Here's the end of 45.5 minutes. And then here's the last 2.5 minutes. So something bizarre is happening about the last 2.5 minutes of the game. And this, I think, lies outside of a random walk description. I have nothing to say about this, but all I can say is it's certainly very weird. Now comes the issue about what is the role of bias. So as was already mentioned, like teams are typically unevenly matched. The Chicago Bulls and when Michael Jordan was on the team, didn't they win 72 games or something outrageous? And they had some incredible, winning streak. But I guess what I would argue is that the lousiest team in the NBA and the worst player on the lousiest team in the NBA is a million times better than I could ever hope to be. So even the worst player on the worst team is an amazing athlete who's been very well trained and very well selected. And the worst team in the NBA can beat the best team on any given day of the week, just if the best team has kind of an off day and the worst team has a great day. So even though the teams are unevenly matched, what I would argue is that they're not that unevenly matched because they've already gone through so many levels of filtration. And so, the teams, the player that was kind of the second best on like the national champions in college might not make the NBA. So I would argue, and I'm going to try and present data that they're not that evenly matched. And in the end, the differences don't matter. So let me talk about the role of unevenly matched teams here.
So
and
Sid,
yeah.
Before you jump into that, I have a question from Ryan Hickox, who says, building on the last question, about winning streaks, which is related to what you're talking about, and thinking about safe leads, does fouling at the end of the game introduce some weird effects that apart from a random walk?
Oh, absolutely. No, there's no doubt it does. But the thing is that, again, this is something that I would, if I had like an infinite amount of time, I'd love to study, is just look at the last 2.5 minutes of the game and analyze it in this random walk picture. We did not do that, but I completely agree that the last 2.5 minutes are completely different because of all the fouling strategy and the deliberate fouling strategy. So yeah, I agree. It's not a random walk in the last 2.5 minutes. All right. So coming now to the issue of bias. So let me do this in the context of like this the time of the last lead change. So we saw that when teams had equal strength, the probability distribution at the time for the last lead change was this thing, the first Arcsin Law. So one can generalize this to not a pure random walk, but a biased random walk. So let's suppose there's a small bias that's quantified by a velocity v, a bias velocity v. And then you have to work a little bit harder, but it's possible to do it. And so this is the analytical expression for the distribution of times for the last lead change when there's a bias. So d is a diffusion coefficient, v is the bias velocity. So it looks sort of horrible. And if you plot it, you see these sorts of curves in the sense that instead of having a symmetrical U-shaped distribution, one has a non-symmetrical distribution. And it turns out that if you look at the bias that's done by averaging over all teams and all basketball games, the true bias in NBA is only 0.004. So it's sort of there, but it's not really a big deal. And then if you look at when you average over all team strengths, one sees that there's sort of you can't really see the difference. So finally, one last point, which is return to zero. So if you look at the scoring probability of a team as a function of its lead size, if a team is losing by 40 points, their scoring rate actually goes up. And if a team is ahead by 40 points, well, they put in the substitutes, the team leaders are are sitting on the chairs, like laughing at the game, their scoring rate goes down. So there is a systematic trend here. So the last part of this talk is I want to show now kind of a very detailed computational model where we try to like put in all the features that we know about basketball and compare it to the random walk picture. So there is a very famous paper in 1952 about the Bradley-Terry model of competition. And the idea here is, suppose you have repeated competitions between teams that have strengths X sub alpha. And so if you think of just like as either a scoring event or a total game, you can ask, what is the probability? Let's look just scoring event by scoring event. If I have two teams, strength X alpha and X beta, what is the probability that team alpha is going to score in a particular possession of the basketball? And in the Bradley-Terry model of competition, the probability that A scores is just the strength of the team A divided by the sum of the strengths. And the probability B scores is again the same, the complementary ratio. So the teams are equally matched, this probability would be 1/2. And the teams are not equally matched, then this ratio will be either larger or less than 1/2. But this is the basic thing that the Bradley-Terry model looked at, is if you have repeated competitions, what are the statistics of the winning and losing streaks? But now we have to include the anti-persistence of the random walk. So this is our work in 2012. So that means that if I score first, then my scoring probability is reduced by 1/6, and the other teams is increased by 1/6, so that that incorporates the anti-persistence. And then there's also this feature that if I have a big lead, then I'm going to score less likely, and if I have a big deficit, I'm going to score more quickly. And again, we plug in the slope of the previous curve, and we have the score difference. And so now we can build a computational model where we take a league of 30 teams, we give them a strength P sub alpha. And so the strength of the teams, we have some choices here. First of all, because the scoring probability depends only on the relative strength and not the absolute strength, we can choose the mean strength of the teams as 1. And then the only parameter in the model is the variation in the strengths of the teams. We also tried this with a square distribution and triangular distribution. It really didn't matter, so we just did Gaussian. So this is the only parameter in our computational model. And so what we do now is we look at many statistical measures about basketball game statistics. We make a team, a league of 30 or 32 teams. I forget how many there are. We have average strength 1. We have this variance sigma, which is the spread in the strength of the teams. And we look at all these different statistical measures. For example, we can look at the winning percentage at the end of the season of a team as a function of its ranking in the standings. We can look at the time leading. We can look at the score difference. And what I'm plotting here, this is kind of a busy slide, is I'm plotting the deviation of our observations by playing, I forget how many seasons. I think we played like 10,000 seasons of basketball. I mean, on the computer, we can do as much as we want. So I think we played 10,000 seasons with 30 teams in the league with this distribution of team strengths given by this. And then we look at the actual data from NBA basketball versus our data. And then we look at, for what value of sigma does all the data match does our synthetic data match the NBA basketball data? And it turns out that it matches at a single value of the width, which is about 0.09. So the conclusion from all of this is that if we start with a Gaussian distribution of team strengths and with a width given by the sigma, which is 10%, so it means that the strongest team is sort of like 10% stronger than the average team, and the weakest team is roughly 10% weaker than the average team. So if we have this distribution of strengths and plus random walk scoring, it accounts for basically any statistical feature of basketball that we can possibly, that we could possibly imagine looking at. So I'm now at my end. I think I maybe spoke quickly because I couldn't see you guys and I couldn't ask questions. So I hope it wasn't too quick. So the question is basketball scoring a random walk? And so what I would argue is I say yes. And then you can decide what you want to say. when I give this talk in New Mexico, because we have like UFO, sighting, allegedly UFO sightings in southern New Mexico, and if you go to the UFO museum in Carlsbad, New Mexico, it's like they'll have here like I only present I present the data, you decide. So this is not quite New Mexico style, but anyways, I say yes, and it's up to you to decide if you believe me or not. So thank you very much for your attention, and I'm happy to take additional questions.
Thanks, Sid, so much. I'm going to clap on behalf of, let's see, the 38 people that are watching. And there are a couple of questions, but, and I'm going to ask them actually, I'm going to give people a voice, which is even better than that. But before we do that, I have a quick question for you, which is the fact that those 2.5 last minutes seem to be so decisive for the end of the game and for the final scoring. Doesn't that throw a bit of a cold water on the analysis of calling the whole game a random walk? Should we be maybe saying most of the games a random walk, but not perhaps the final?
Yes, I completely agree with you. Yes, it does throw some cold water on the statement that basketball scoring is a random walk. So if I wanted to be intellectually honest, I'd say the first 45.5 minutes of basketball scoring is a random walk. So you're absolutely correct.
I know. It's not as exciting. I agree.
Not as exciting.
But it's really fun. One thing that Sid does, is he really has fun with physics, which I think is a wonderful trait of his. So, okay, now questions from the audience. So Christina Lynch, Christina, let me see if I can find you. No, I have to kind of find you here to give you a voice. It's kind of annoying. Hold on. Where are you? Okay, Christina, there you are. Allowed to talk. Okay, Christina, I think you should be able to talk now.
Hi, thank you so much.
Sure.
Yeah, I'm wondering how this analysis maps to other highly prepared professional team sports that are low scoring, such as soccer, where a game has a score more like 1-2 instead of 99, 101. I think there must be an analogy.
Absolutely. So in fact, we did do the same kind of analysis for other sports. And the only one where we could begin to see the hints of what we see in basketball was in American football, where, you could have like a game which has like 4 touchdowns by one team and 3 by the other and 2 field goals. So all I'd say is that if we could have 1 million years of data, then maybe one could see some of these effects in things like professional hockey, professional soccer. But those unfortunately are very low scoring events. So you can't use like random walk picture is useful when the number of steps is large. And so 100 steps seems to be about as small as you can get and still see like asymptotic effects. So unfortunately, ice hockey and soccer, no dice.
But wait, as a Brazilian, I have something to say about soccer. So maybe the way to frame the problem is not in terms of scoring, but in terms of passing, the frequency of passing, ball control.
So in fact, this has now become a really hot subject because people are now putting GPS devices and everything. There's actually in hockey now they try to put GPS devices on the pucks, and boy, I want that data. I really want to use. I want to look at it through my random walk eyes. So yes, I think that the kind of thing that would be simple to look at is like where is the position distribution of the ball. And I think this is something where, yes, there will be a lot of data sometime soon. And yes, I'm gonna go after that data.
Yeah, that's good. Length of passing, soccer is fabulous for that. Okay, there's one more important question here. Did you examine overtime games? Is this the last 2.5 minutes? Does that also apply?
No, we did not look at overtime, because we felt like it's a different game altogether, and also that meant that the length of the games is not constant, so we did not look at overtime.
Okay, great. Audience, any more questions from you guys? Let's see.
I see another face showing up, so I don't know if that means there's a question.
Let's see. I'm trying to follow here. Yes. Okay, somebody's saying the Arc Sine Law is ubiquitous. Many phenomena involving a deadline show rates that are well described by the 1/square root of t, big T minus small t. Any comment?
Well, I mean, thing is that when you have situations with a deadline, that's sort of like the second tail of the arcsine, but it doesn't say like, you know, it's like the example I'm familiar with is like if you look at abstracts submitted to the annual, you know, APS meeting, and in fact, they actually did analysis of it. Like everybody submits their abstract at the very last second. And so the number of abstracts seems to have this 1 over square root of t singularity, but there's nothing like when you open up the site to allow for abstracts to be submitted, there's not a whole bunch of abstracts showing up at the very beginning. So this thing about what happens at a deadline is a different phenomenon than the Arcsin Law, which has 2 peaks, not 1 peak at the end.
Got it. Okay, thanks. There's a question from Riley here. It's a funny one. Have you done any sports betting based off this? And if so, was it profitable?
So no, I have not, but you know, especially when I gave this talk in England, I mean, I think some people, you know, because there they have real-time betting. So I think that maybe some people are, you know, maybe applying it, but, you know, like, I don't really care about sports. You know, I'm a fan of sports statistics, but I'm not a fan of sports. Sorry.
So this painting behind you is not a $10 million painting that you bought from betting on basketball, okay?
No, it's a free download of the group of 7 paintings.
Okay. And then apparently one more question. Is the scoring of a single player also a random walk?
We do not have that kind of data because all we had was the score as a function of time, not individuals. And so I don't know what to say there. But one thing I would say is that most players do not play the full 48 minutes. And so their scorings are, I don't know how to describe it when they're in the game or not in the game. That's another issue, like how to properly normalize that kind of data.
Yeah. And I have one more question. Jim, you have a voice. Do you want to ask?
Really? I didn't realize that. Well, I was just going to sort of say, well, we all sort of laughed at that bookie, you know, whose model was so far off for the safe lead. But the deviation is so drastic from random walk in the last few minutes. Is it possible that you know, if you analyze that his model might actually be better, you know, if at the end time approaches, last 5 minutes?
I mean, all I can say is that plot of like the probability lead is safe as a function of time, that went all the way to the very end of the game, and there was no anomaly associated with like end of the game shenanigans. I mean, it seemed like it worked very well even up to the end of the game.
Okay, so we can laugh at him after all then.
I think so, yes.
Yeah, well, I don't know.
He's richer than I am.
He's probably very rich, so I'm not sure I'll be laughing too much sometimes.
Yeah, exactly.
That depends on the story you tell. All right, any last question, anyone? I don't see.